Hello everyone, welcome back to this lesson. We're still looking at applied problems. We just finished question number 2 on page 37. I'm looking here right now, this is on page 38, question number 3 at the very top of that page. And I'm thinking this question is practically identical to question number 1 on the previous page. The entrance to a building is a parabolic arch, 5.6 meters high at the center, 7.4 meters wide at the base. So basically we have, well, something like this. Let me get my pen going. All right, we have something like this. Here's your base. Here's the arch again. Okay, it's like the arch, the entrance to a building. It's 5.6 meters high at the center, 7.4 meters wide. So from here over to here, that is 7.4 meters. Yeah, I'm thinking we're going to set this up in exactly the same way that the other one was set up. Okay? Uh, what equation represents the arch if the vertex is at the top of the arch? Well, obviously that's kind of true anyway, isn't it? Nothing surprising about that. So again, here's the way we should set up all of these arch type problems. Have the x being the base and have the vertex right on the y-axis. So that point right there, now remember, that's actually 5.6 meters high. So the coordinates of that point is 0 and 5.6. Actually, I think I might just leave this one for you to try because, like I said, this one is practically identical to question number 1. The width of the arch is at the base, 7.4 meters. So if you take half of 7.4, half on either side, of course, then this point right here should just be what? Half of 7.4. 3.7 and 0. And of course, the other point on the other side, think of this as your x-intercept. That's negative 3.7 and 0. Yeah, you know what? This is exactly like the one we just did. So again, what you would do, I think I probably will leave this one for you to try. You can see that it's opening downward, so it's going to start x squared. I'll just set it up for you and I'll let you finish the rest of it. So it's going to be x squared equals 2. Now remember, there's going to be a constant in front. Actually, you know it's going to be a negative anyway. You don't need to put a negative in front right here, though. You can just put 4p there. You know it's going to turn negative eventually when you work it out. And let me see, what about the y coordinate? Okay, so that's y minus 5.6. All right, now, yeah, I think I will. I'll leave this one for you to finish. There is what your equation starts like. That's definitely the form of it. Now, notice I didn't put a negative in front of the 4p. I don't really need to because when you work out 4p, it's going to become negative anyway. Can you see a point on that parabola that you should plug in here? Well, yeah, like one of those x-intercepts again. 3.7, put that in for your x, and 0 for the y, because that point, remember, is on the parabola. So if you plug that in, you get your 4p. And like I say, when you work it out, it's going to be negative anyway. And it's supposed to be negative because your parabola is opening downward. All right? So you finish that one. You finish that one right there. I'm going to have a look at number 4. Number 4 is about a topic that's very, very dear to my heart. This is about astronomy. Astronomy is a big passion of mine. I once had a student ask me about a year ago, why do we learn all this stuff? What's in this? What is so interesting about conic sections? Like, when are we ever going to learn it? Well, we've just seen some types of word problems we can solve with it. But everything in our solar system, for example, everything, every single body orbits the sun. If it didn't orbit the sun, then technically it's not part of our solar system. And every single object that orbits the sun orbits in an ellipse. Everything. I know some of those ellipses are very, very close to being circular. For example, the orbit of the Earth is pretty circular, but it's not 100% circular. It's actually an ellipse. We're closer to the sun during the winter, actually, than we are during the summer. Other objects, you ever hear of an object that visited our solar system about a year ago or a year and a half ago, maybe 2 years ago, called Oumuamua, right? They said it was extraterrestrial, came from outside of our own solar system. How do they know it came from outside of our solar system? How do they know that? Because its orbit wasn't elliptical. Its orbit was actually hyperbolic. So that meant that it didn't originate in our solar system and it's not going to end up in our solar system. Let's read number 4, see what it says. I can get on astronomy for hours. A space object larger and more distant than Pluto was discovered in 2003 in its elliptical orbit. Like I said, everything is elliptical, everything in the solar system, with the sun at one focus, and that's true for all of the objects, by the way. The sun is at one of the foci. It is 3.5 million miles from the sun at its closest point and 9.0 million miles at the furthest point. What's the eccentricity of this orbit? Well, now remember, eccentricity is equal to c over a. That's the formula for eccentricity, right? So if we set up a simple diagram here, watch what I'm going to do. I'm going to draw an ellipse. Let's just pretend that this is the orbit of that object they're referring to. Okay, and let's suppose that one of its foci, I'm going to put the foci right there approximately. I'll put a little letter F there. There's your foci. And of course the foci lies on the major axis, so I can even draw the major axis there. Something like that. But there's a foci, and I'll just put the center about right there. Okay, now let's fill in some numbers, shall we? It's a space object larger and more distant than Pluto, discovered in its elliptical orbit. The sun is at one focus, so there's the sun right there. Okay, that's supposed to be an S. There's your sun right at the focus. It is 3.5 million miles from the sun at the closest point. So that right there, that is 3.5. Now I'll just put down 3.5, but remember that represents 3.5 million miles. Okay? And then at its furthest point from the sun, well, the furthest point from the sun would be way over there. That's when it's furthest away from the sun. It's 9 million miles away. So again, 9 million. I'll just put down 9.0. But remember, that represents 9.0 million miles. Now, what's the eccentricity? Well. How do we get the eccentricity here? Because there's very little given, isn't it? It's very little actually there. Now, I tell you what we could do. If this is one vertex right there, that's where this object is at its furthest point. And there's the other vertex right there, and that's when the object is at its closest point, you see? Well, if I were to add those two distances together, that would tell me the distance from one vertex to the other, and that's actually the length of my major axes, all right? And not only that, here, let me put that down. Major axes is equal to 3.5 plus 9.0, and that's supposed to be a 0. So that's 12.5. Now remember, that represents million, 12.5 million. Now, if that's the length of my major axes, remember, that's 2a, isn't it? That's 2a. So if I were to divide that by 2, a should be 12.5 divided by 2. And if my old memory serves me correctly, that should be 6.25. There's your a. You see that? So that's the distance from the center to this vertex, and the distance from the center to that vertex right there. 6.25 and 6.25. But wait a minute. If this is 6.25 million, remember, and this little piece there is 3.5, then I should be able to get the distance. Let me clear up some of this. It's kind of a little bit cluttered up. I should be able to get the distance from this focus to the center by doing a subtraction. That's my C. So C would actually be equal to, let me see, 6.25 subtract 3.5, and if I'm not mistaken, That should be what? 2.75 million again. 2.75 million miles. Now, there's my C, and there's my A. Well, you know what? This was actually fairly straightforward. There was no big calculations involved. Now, remember, these actually stand for, those decimals stand for millions of kilometers. But if I were to take those numbers and multiply by 1 million in the numerator and denominator, the millions would cancel anyway. So C over A is 2.75 divided by 6.25. Remember, eccentricity is always less than 1. Now, what would you get there? What would you get there? Well, let me get my calculator. If you were to get that as a decimal, 2.75 divided by 6.25, look at what you get. 0.44. There's your eccentricity. There is your eccentricity. So that wasn't a bad problem at all. That wasn't difficult at all. And like I said, there was no big calculations involved. Just understanding where the C was located, where the A was located in our diagram. You didn't have to know anything about astronomy. Question number 5 is practically the same as question number 3 on the top of the page and question number 1 on the previous page. But there's a little something about this that I want to point out. This is a very important type of a question. I think I'm going to actually do this one quickly so that we can see how this one here actually works. A tunnel is built in the shape of a parabola. Okay, there's your parabola again. The maximum height will be 13 meters and the maximum width is to be 12 meters. So in our diagram, let me put that in. This width is 12 meters. And if I were to put in my, y-axis right there, right through the vertex, pretend that's a straight line, then that maximum height was, what did they say? 13 meters. So that point is 0, 13. This parabola, we have to get its equation, is still opening downward, isn't it? And the vertex is still at the very top. So what is the vertical clearance? What's the height of the tunnel? 4 meters from the bottom edge. Now that's what's different about this question. Look at that. If you were in this tunnel, if you were stood up inside that tunnel, if you were 4 meters from this point, from the edge right there, what's the height? What's the headroom in that tunnel? What is that height? All right, well, I'll tell you what. The first thing you're going to need is the equation of that parabola. So it opens downward again. All right, so it's x squared equals, all right, and I can see that the x-coordinate of the vertex is 0. And I'm going to put a 4p there again. Now, yes, I know it's negative. Yes, I know. But it'll work out to be negative when we calculate it now. In fact, you could just put something like an a there if you wanted to. It's just a holder for the coefficient, you see. And then this part becomes y minus 13. Okay, so what I'm going to do now, remember, it's 12 wide on the bottom, so this point here is 6, 0. And this point over here, although we don't need that other point, it's negative 6 and 0. All right, so I'll plug in, say, 6 and 0. Or now you could plug in negative 6 and 0 if you wanted to. So 6 goes in for x, that becomes 6 squared is equal to 4p, 0, subtract 13. So all you're really going to do here is you're going to square the 6, and that becomes 36. But then you're going to divide both sides by this negative 13, you see? Now you can leave it like a fraction if you wanted to, or you could write it as a decimal. But now do you see it? It's negative, isn't it? I told you it was going to be negative. It's definitely going to be negative. So your equation actually becomes, where can I find some room to write that? Let me write it here. X squared is equal to negative 36 over 13, or change it into a decimal if you want, times y minus 13. Now there is the equation representing this this parabola. Okay, this tunnel. That will tell you the height at any point inside. Now here comes the tricky part, and it's not really tricky, but it's something you had to be aware of. If you want to get, I'm just going to erase this to free up some room here. If you are going to put in this point right there to find the height, what x value are you going to put in? Are you going to put in 4? Is that what you want to put in? Because if you do, you're not going to get the right height. Remember, what you're plugging in is the x value. This point right there, that, everybody, is your origin, isn't it? That's the 0, 0. So at this point right there, yes, it's 4 meters from the edge of that tunnel, but x is not 4, right? At this point, x is 2, because remember, the distance from the center to the edge is 6. This point here is 4 meters from the edge, so that piece right there, that's only 2 meters from the center. You've got to plug in x equals 2. So it's very important that you read the question there. Very important you look it over and understand what they're asking for. Okay, what they're expecting you to do. So if I took that equation and put in x equals 2, watch what's going to happen. Let me erase that other little bit right there. I need to free up some space. So back up here, you're going to have 2 squared is equal to negative 36 over 13 times y minus 13. All right. 2 squared is 4. Multiply both sides by the reciprocal of negative 36 over 13. So that's going to be 4 multiplied by, and the reciprocal of negative 36 over 13 would be negative 13 over 36. See? Is equal to, and now it would cancel on this side, and all you have is y subtract 13. So now you take your calculator, type all of this in. I know you'll get a fraction, but you can change that into a decimal if you like. All right? And then when you bring your 13 over from the right-hand side, it'll become plus 13. Now when you type all of that in, here's what you're going to get if you do it correctly. You're going to get approximately 11.6 meters, and that's your height. Now look at your diagram. Do you think that's logical? Do you think that makes sense? Is 11.6 a reasonable answer for this question? Well, remember, the maximum height of the tunnel was 13 meters. 2 meters is not that far. I know it's a little bit distant, but it's not that far from where the center of the tunnel is, and that's where the maximum height occurs. So if this height right there is 13, does this height look like it might be about 11.6? You know what? Yeah, it sure does look reasonable, doesn't it? That looks very reasonable, in fact. I have no reason to question the validity of that solution. And that looks like what's going to happen there. So please make sure you understand that type of a question. I've seen that type of a question come up so many times on tests or quizzes. It's important you know what to do, not just to get the equation of the tunnel, the parabola, but to also know, like, what x value are you supposed to put in? If that question had said, what is the vertical clearance of the tunnel 4 meters from the center of the tunnel? Now that's different. If that had said 4 meters from the center, then yes, that would be over here somewhere, you see? And in that case, you really would put in 4 for x. All right, what else do we have here? Here's another type of question I've seen a lot. In fact, I've given this one quite a bit, but this question is actually worded slightly different from the way I usually give it, the way I typically give it. This says the Golden Gate Bridge in San Francisco is a suspension bridge. Its supporting cables are parabolic. Look at that, more parabolas. With the origin at the low part of the cable, that would be right there. Now see, that's what's different from my questions. What equation represents the cable if the towers are 1,280 meters apart and the maximum sag is 90 meters? So the way they've set it up, everybody, seeing that the origin is on the cable, your x-axis should look something like this red line. You see that? It's actually going through that point. Now that's the way they've set this problem up. When I give a question like this, That's not what I usually ask. I usually have the x-axis as the ground, or in this case it would be as the actual bridge, and I actually give the distance from the ground up to that lowest point. All right, and also the heights of the two towers as well. And then you can actually set it up so that this point is not the origin, but it is the vertex. So if this height was, say, 10 meters, then the vertex actually occurs at 0, comma 10, because that is still the y-axis. The y-axis still goes down through the center. All right. So be aware of questions like that. Anyway, you try this one. Also, number 7, telescope. Another one right up my alley. Number 8, stream of water from a fire hose follows. Look at that, another parabola. Number 9, the vertical cross section of a culvert under a road is elliptical. Oh, finally, we have a question about an ellipse. Try this one as well. Remember, make a diagram, fill in your information, see what happens. And number 10, wow, this one looks kind of tricky. A lithotripter is an elliptical-shaped device used to break up kidney stones by focusing shock waves directly on the stone. If the device is 30 centimeters long and 6 centimeters wide, so in other words, that's 30, and that is 6, so that's your major axes and your minor axes. How far apart are the foci? Well, actually, you know what? That's not very difficult. That's not very difficult at all, because if you know that your major axis is 30, and that's 2a, that tells you that a is half of that, so a is 15, isn't it? And if the length of your minor axis is 6, then that tells you that what 2b must be 6, so b is equal to 3. And by golly, you know now you can get your c really easily. For an ellipse, remember it's a squared minus b squared. So c squared would equal 15 squared minus 3 squared. Okay. So that would be 225. Subtract 3 squared is 9. C squared would equal 216. Now you could give the answer there as a radical if you wanted to, a simplified radical. Or you could even just give it as a decimal. If you give it as a decimal, I think you're going to get approximately, you take the square root of 216, I think you're going to get about 14.7. 14.7, and that's centimeters. So that's the distance from the center to one focus, right there. But it's also the distance from the center to the other focus at about right there. So the distances between the two foci is double that. So the distance here would be 2 multiplied by 14.7, and that should give you about 29.4 centimeters. But no big math, nothing really complicated there to actually work out, all right? And that's the last question. So I'm going to leave the other ones for you to try. Give them a good try. If you have any difficulties, please make sure you pop me an email, ask me about that, and I'll certainly answer any questions that you might have, okay? And that's it for unit number 3. So I guess we have a test coming up very soon. We'll also be starting unit number 4 very soon, so please make sure you print off a copy of the unit 4 notes for that. And I'll stop right there. All right, so have yourselves a great day. Bye-bye.